Dear students, in last class we have discussed a brief introduction about a self-inductance and how you will get a induced EMF from the circuit which is connected to the that circuit of a coil. And in this class we'll discuss that is the derivation of self-inductance or derive an expression of self-inductance, so which is we have taken L. So before going to this expression, to derive this expression, briefly we will see what is the self inductance and how you will get a EMF from the that circuit. If we consider the definition here, the phenomenon of the induced of EMF in a coil to the change in the same coil itself is called as self inductance. So we have used this animation and I will take the picture of that animation here. We have used a battery which is connected one of the cylinder of the coil, and we have taken a one bulb here, and we have connected a tap key, otherwise you may call any one of the key. So here this circuit is in series. So if we connected all these things in series and we are going to pass the electrical current, when key is closed, a current in a circuit is rises from 0 to maximum. So current is rises from 0 to maximum in a certain finite time, up to where, up to, for example I will take here, that is if I took a EMF is 10 volt, EMF is 10 volt, and whatever the resistance is there, that a resistance is 5 ohm resistance in this circuit. So before connecting this coil, I have taken 10 volt and 5 ohm resistance. So if I calculate the current, then you will get that is 10 divided by 2, 5. Here you will get 2 ampere. So 2 ampere current is passing through this circuit. So if I closed the key, then suddenly what will happen? The bulb is blowing when if the coil is not connected in that time. If I open, then again it is going to off. So completely 2 ampere it is flowing through the that circuit. Instead of that one, I am connecting this cylinder. This is called as a cylindrical coil, and now if I close the key, then current is passing through this circuit, and that current is passing through completely all these coils. So here the bulb is blowing from 0 to the maximum intensity. Already I have shown in last lecture. So why it is, and now what will happen, it takes to blow completely 0 time to the maximum time. It means, for example, I will take, I have opened the key, closed the key, and then in that time is 0. So and whenever that bulb is blown completely, so in that time the time is 0.15 microsecond or 1 microsecond, or any of the time is going to be take to blown a bulb completely. So why it is taking the time? So that is due to this effect. So that is the flow of current is opposing from this coil, and here the coil is nothing but the inductance, and that is this inductance is producing the that magnetic field, it is producing the that EMF is opposing the to flow of that current. So here the if the current is flowing from the 0 to maximum, so in that magnetic flux is generated. If the maximum current is there, then maximum magnetic flux. If the current is less and then minimum, then the magnetic flux is also minimum. So therefore here, that whatever that magnetic flux is there, that is depends on the current, and that is gives the phi is directly proportional to the I. So I will read that one. That is the expression. If I close the key, the current in the circuit rises from the 0 to maximum. In a certain finite time, the magnetic flux is linked with the coil is also increases. As a result, EMF is induced in the coil. The EMF is opposes the growth of the current in the coil. Whenever the tap key is released, the current in the coil decays from the maximum to 0. The flux linked with the coil is also decreases from the maximum to 0. As a result, an EMF is gained induced in the coil. This EMF is opposes the decay of current in the coil. So this EMF is induced in a coil. When the current in the same coil changes, the phenomenon is called as self-inductance. So let us now derive this expression. The self-inductance expression, that is L equals to what you will get. Let us take here a cylindrical coil which is connected to the battery, and we'll connect one tap key here. So this is a battery, and this coil is having the length L. The current is flowing through the circuit, and the coil is having the area A, and this coil is having the number of the turns per unit length. If the current is flowing through we can consider this is a solenoid. Through a solenoid, the magnetic field is inside a solenoid is almost constant. Whatever the magnetic field is there inside the solenoid is almost constant. So therefore the magnetic field, the solenoid, is mu naught n into I. Already we have derived this one. Now we'll consider this is as a solenoid. So the solenoid expression of the magnetic field is mu naught n into I. Now what will happen if the current is flowing through the that solenoid? The magnetic flux linked with the solenoid is given as so flux is a phi. So here number of the turns is there, n number of the turns, and the magnetic field is linked to the area along with the angle, so cos theta. So theta is, now see here, this is the direction of magnetic field, and now here theta is becomes 0. So theta is 0, then pi equals to n b a we can write. So and therefore n is number of turns per unit length is there. This is the n of the number of the turns per unit length. We can write capital N is equals to n into L. So therefore pi equals to n L will write n L. B I have taken here, B is mu naught n into I into area. So this pi becomes n square L into mu naught into I into A. This is I will call equation 1. We know that pi is directly proportional to the I, where when the current is flowing through the that cylindrical coil. So that is flux is directly proportional to the current. How much flux? If the flux is if the current is increases, then flux is increases. If the current is decreases, flux is decreases. So it depends on the current. So we can write this one, phi is equals to L into I. Phi is equals to L into I. So therefore here we can write this is equation 2. So Li is equals to the n square L into mu naught into I into A. Here I get cancelled. Then what remains? L is equals to the n square into L into mu naught into A. Mu naught into A. So this is the expression of self-inductance. We'll give this equation number 3. So now here this solenoid is there. I have taken that solenoid. That solenoid is, if you not wounding on any one of the material, then it is gives the mu naught only. If you are wounding on any one of the material, I have taken iron. I have told that is iron, wounded on iron. That's why if the solenoid is coil is wound on a core of some magnetic material, iron, otherwise you can call soft iron, like that, then the expression becomes L equals to mu naught into mu r n square L into L into A. This expression we can use. So here we will write L is a self-inductance, and mu naught is permeability of free space, and mu r is relative permeability and L is length of the solenoid, and A is the area of the solenoid. So N is number of turns per unit length. So it means, what it indicates, the inductance, self-inductance is depends on the permeability of the free space and relative permeability, and here the length of the solenoid and area of the solenoid, number of the terms of the solenoid. But it does not depends on the current. It depends on all these parameters. So this is the expression of self-inductance which is we have derived here. So it means the L is directly proportional to the mu naught and mu r, and L is directly proportional to the square of the number of terms, and L is directly proportional to the length per unit of the that wire, and L is directly proportional to the area of the solenoid. Thank you.